for today's what we call heap sort. You see, the first point about heap sort that you can that comes, that is a heap sort, a heap actually. Before we uh, understand this heap sort, we have to understand what is actually heap. We can say that a heap is a complete binary tree. Now, what is complete binary tree? That already I have discussed when I started the class of tree. So you can, if you have, if you want to revisit this concept, that you can go to my previous videos and check it. But still, if we discuss this complete binary tree in a nutshell for this class, we can say a complete binary tree looks something like, for example, something like this. Now, what is the property of a complete binary tree? That each and every node will have at most two children, and all the leaf or all the nodes before the above the last level of the tree should be completely filled. And the third point is that the node should be filled from the left to right. Now that means if you somehow include another node over here, this tree will no longer remain a complete binary tree. To make it complete binary tree, you must have another node somewhere over here also. And in the next level, if you consider the next level after this leaf node, the first node should be inserted as a left child of the leftmost node of this level, that is somewhere here. Now, how you can understand, how you can find that whether a tree is a complete binary tree? To realize this, one more point you have to remember, that is how we can represent a tree in an array. So suppose I have an array something like this, and I want to store the value of the nodes present in the complete binary tree somewhere over here in this particular array. In that case, we have to remember something about their relation between different nodes. For example, A is parent of B and C, and B is left child of A, C is right child of A, and similar type of relation is present for other nodes also with respect to some of the previous nodes as a parent. So here you remember that this array index may start from 1 or may start from 0. It depends upon totally you. If we consider, so if index start from from 0, then if we consider that parent is present, say at ith index, then left child should be present at 2 into I plus 1th index, and right child should be at 2 into I plus 2th index. And in another way, that if I consider that the index starts from 1, then you can say that if the parent is at ith position, then left child will be at 2 into ith position, and right child will be in 2 into I plus 1th position. So let's take an example for a complete binary tree. For example, something like this. So if we have a complete binary tree, looks something like A, B, C, this side D, E, F, G, and suppose we have H and I. And if we have an array, how many data is there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So the array that we have, we must have at least 9 locations, right? 4, 3, 7, 2, 9. Yes, 9 locations. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. So if we start from 0, 1, 2, 3, 4, 5, 6, 7, 8. So array starts from 0. So according to the rule, we have to maintain this one. So let's take that I will start our root in the 0 position. So if A is here, so left child of this one, so that means I is 0 with respect to this A, right? That means left child of A, that is B, should be present at 2I plus 1th index, right? So that means 2 into 0 plus 1, that is equal to 1. That means here B should be present. Similarly, with respect to A, it should be, the C should be at 2I plus 2. That means 2 into, I'm sorry, uh, 2 into 0 plus 2, that means 2. Somewhere here C should be present. Similarly, you see, with respect to this part, B, D and E, B is the parent, right? And position of B with respect to this array is 1. That means with the same situation, the left child of B should be present at 2 into 1 plus 1. That means 2 plus 1, that is equal to in 3. That means D should be somewhere here, and obviously E should be somewhere over here. In a similar situation, you see that if we consider this part, this is a part of the tree where C is the parent and position of C is 2. That means left child of C will be at 2 into 2 plus 1. That means at 5 index number 5, that is F should be somewhere here and G will be here. Similarly, if we consider this particular part, position of D is here, you see 3. That mean 3 into 2 plus 1, that is 7. Here 8 should be present and here I, right? So one thing we can see over here, that there is no gap between these elements within this particular array. For example, we know that this is a complete BST, correct complete BST. But I'm sorry, yes, complete BST. Now let's take another situation. For example, A, then B. Here we have C, and maybe then D, uh, and maybe here I have E. Suppose this is obviously not a complete binary tree, but if we want to do the same thing for this case also, I mean, I want to put this nodes, value of the different nodes of this particular tree in an array, then, and if the array starts from 0, you see what will happen. So we have a number of locations over here, maybe it will exceed the number of values present in this tree. However, it doesn't matter. So first let's numbering it, fine. And you see, obviously A will be somewhere here, and this B and C will be, you can easily calculate that B and C will be here, and left child of B, D, will be in, I mean, position of B is 1, so 2 into 1 plus 1, that is equal to 3. Somewhere D will be here, right? And E will be where? E will be on, E is the left child of C and position of C is 2. That means 2 into 2 plus 1. That means 5. So here E will be there. Now see, the difference between these two cases is that we have a blank part within the array. So if someone asks you that just prove it that or find it whether a complete binary tree, I mean a binary tree is really complete or not, then what you can do, you can simply try to put in the same in a similar way in an array, and if you find something you, I mean even a single blank present within this data set, then you can say it is not a complete binary tree. Now, why I am saying this one? Because we know that heap is a complete binary tree. The question is that how we can, I mean, I mean, what is the different, I mean, type of heap possible? Heap, I'm sorry, uh, yes, we can have, just a minute, a heap, uh, a heap tree can be of generally two types. One we call max heap and another we call min heap. Now, what is max heap? Max heap say that in each and every subtree of a complete binary tree, the parent will be greater than its child. What I mean? I mean that if we have a situation something like if we want to create a max heap, so for example, I have a 50 value over here, these two sides, the left and right child of 50 must be lesser than 50. You see, don't mix up the concept with a binary search tree. We are not considering binary search tree over here. So that's why you cannot apply the rule that left child is lesser than the parent and right child is greater than the parent. This rule is not applied over here. It is a simply binary tree we are considering, which is complete. And that's why it will follow the rule that already we have discussed. Now, in case of max heap, as I told you, that the value that present in the left and right child of 50 should be lesser than it. So maybe, in this side we have say 40 and in this side I will have a 30. And if there is a child of 40, then also the child value should be lesser than this 40. That means maybe it contains say 10 and it contains 20. And this side may contain say 25 and this side 5. So basically there is no relationship between one one subtree in left side with the another subtree in the right side. You cannot make any relationship between them, but a basic relation that you can say that for each and every node and corresponding their childs, you can say that parent is greater than is its right child. At the same time, parent is greater than its left child. But there is no relationship made between right and left child. There is no relationship present. So in case of, so this is an example of a max heap. And in the max heap, what you can see that the root of the tree is basically contain the maximum value. Okay. In a similar way, if I want to design a min heap, it will be just an opposite situation. We can say that parent is always, lesser than its childs. That means if parent may contain, say for example 5, the child of this one, maybe this side will be 10 and this side will be 20. Similarly, the if you consider that 10 has some childs, the child value should be greater than this 10. That is, say for example here, I mean 15 and here 25. And this side, maybe if there is something that will be again greater than this 20. So for example, say 30 and 40. And here the main uh, relation between each and every subtree of this whole tree, that is parent is lesser than left child, as well as at the same time parent is lesser than its right child also. But there is again no relation between left and right childs. So what I can find out from these two different cases, if I just put them in a say array, okay, so what will be the data over here? Here will be, we will have 50, then 40, then 30, then in this side we will have 10, then 20, then 25, then 5. And if we put them in array this part, it will be something like 5, then 10, then 20, then 15, then 25, then 30, and then 40. So what is the basic difference? We can find this from maxheap and minheap. In case of maxheap, the first element of the array contains the maximum value. In case of minheap, this is the minheap, right? In case of minheap, the first element contains the minimum value among the whole set, but there is no relation between the other values. Now the sorting technique that we are going to face over here will be based on this situation. But before that, we have to understand one more thing, that is how we can insert operation. We have an insert operation on, for example, maxheap. So if you understand the insert operation of maxheap, I hope the insert operation for a minheap also will be clear to you. So let's take the similar, strategy, similar data over here present. So the maxheap contain here 50, then 40, and in this side I'll have 30, and this side he has 10, 20, 25, 5. So it contains 10, 20, 25, and 5. Now see, if someone asks you that if I want to insert, say for example 35, question is that where I will insert this 35. You see, if you say that 35 should be uh, before, 35 can be actually in between 10 and 40. It's possible. If it was something like 40 left side is 35 and 35 left is 10, then also it is okay. And in this side, if you say that okay, don't think 35, take consider a situation which is say 60, which is greater than the maximum value present in the tree. So if I want to insert 60, obviously 60 should be on the root. So what you will do, you will put 60 over here, and you will just 50 will be down, 40 will come down, 10 will come down. You cannot do in this way, because you don't know about this part, this side. There is no relationship between 40 and 30. That is why always remember, we insert a node as a leftmost node of any level if it is not created. For example, if 5 was not present over here, for example, I mean what I mean to say is that if I have a array, I mean if I represent the tree as an array, so the data will contain, as you know, it will contain 50, 40, 30, then 10, 20, 25, and suppose this 5 is not present over here right now. Okay, 5 is not present over here. In that case, always remember, whatever data that you want to insert in the tree should be first inserted at the end of the array. That means 60 should be somewhere here. So if 60 is here, so with respect to this tree, 60 should be, the newly inserted data 60 should be somewhere here. But we all know that if inserting 60 over here is violating the rule of max heap. So accordingly, we have to continue. What we will do here, we will see very soon. Now, in the real situation, we have already some data over here, right? So we have already some data over here that we know, that is 5. So instead of 60 over here, right now, here we have 5. And suppose the array is little bit large enough to store many other data, which ultimately will represent the part of the tree. Okay, now if I want to insert 60, always remember, since this last level is already filled up, so 60 should be inserted according to the rule of complete binary tree. 60 should be inserted at the left child of this particular node 10. So according to that, the new value should be somewhere here. But yes, again it is violating the rule of the max heap. So basically what you will do, you will check this 60 with 10. That I don't know about the other part, but what I know, at least this 60 and 10, whether are they following the proper rule of a max heap? No, they are not following proper rule of max heap. So that's why what will happen, we will have a swap between 60 and 10. So that means the next new updated situation of this particular array will be something like 50, then 40, then 30, then instead of 10, 60 will come, and 20, 25 remains same as it is, 5 will remain same as it is, and here the 10 will come, right? So the situation something like it happens something like the newly formed tree will be 50, 40, 30, 25, 5, here it is 60, here it is 20, and then 10. Now question is that wherever 60 has come, 60 has some parent also. Over here at least I can see. So now what I have to check it, whether this 60 is and its parent is following the rule of max heap. Still we can see that they are not following rule of max heap, because 60 should be somewhere over here. I mean 60 should be actually parent of 40, right? So that means, just like we had a swap between in this with respect to these two situation, these two data, we will have a again swap between these two data, and ultimately what will happen in the array, it will be something like 50, then instead of 40, 60 will come, and then 30 remain in its place, and here 40 will come, and then 20, 25, 5 and 10. So and then the newly updated tree will be something like 50 will be here, below this it will be 60, below this it will be 40, and below this it will be 10. And in the side of 60 we will have 20, in the side of 30 we will have same situation 25 and 5. But still there is one more thing to check whether 60 and 50 is violating, following the rule or not. But we can see that again we are violating the rule, so we will have a swap between 60 and 50, and ultimately 60 will come here and 50 will come here, then 30, 40, 20, 25, 5 and 10. And ultimately what I will find out, we will see that 60 has come in a root, then 50 here, then 30 this side, then 25, then 5, then 40, then 20, and then in this side you will have 10. And now this particular BST, you can say it's a complete BST where each and every node is maximum is greater than actually than its parent, than their child. So that means this particular tree is not only a complete binary tree but also it is a massive. Now just try to realize the change of the position of 60 throughout this array. So 60 was initially somewhere here, and suddenly here it jumped from this position to this position, then from this position to this position, I'm sorry, this position to this position, and then from this position to this position, right? Now if you just consider the index values, so you see that it is 0, it was 1, it is 2, this is 3, this is 4, 5, 6, 7, right? Now see, if you check the index values, the newly created index values with respect to the previous one, you see initially if 60 was in ith index, next time it changed to I by 2 index, the floor value of I by 2, right? Because it was 7 by 2, that is 3, then it changed 3 by 2, that is 1, then 1 by 2, that is 0. So basically with respect to this tree, what you can see, you started jumps from here, you jump to this position, then jump to this position and jump to this position. You don't need to go through this other part. So you see, since the value that I have just inserted, which was the maximum one, then the root of the tree, root of the maxive, the present maxive, that is why we had a journey like this. If I consider instead of 60 it was 35, then obviously up to this 0th position 35 will never come. This 35 will stop over here. So that means if I try to analyze that what is the maximum time taken by this insertion algorithm, it is actually taking the time with respect to the height of the tree, right? Because this is the height, this is the height of the tree, because this is the last level. And what we know, we know that height of a tree is always in an order of log n. That means we can say that insert operation, insert in max heap, follows an order of log n. So this is the worst case scenario. But what is the best case scenario? What is the best case scenario possible? The best case scenario possible if the data that I have just inserted, for example 5, for example 3, since 5 is already there, so I am taking one lesser value, say 3. And if it is 3, and if I insert over here, I will see that 3 and 10 is already fulfilling the criteria to be a max heap. And if 3 is lesser than 10, so it's very trivial that 3 will be lesser than to all other its parents, corresponding parents till the root. So basically there will be no replacement required or no swap required. So that means in that case, in a best case, so this is what we call, actually what I can say, a worst case scenario, right? But in case of best case, the scenario will be a constant time. That means I can say it will take big O of 1. So that's why, that means the insert operation for a max heap take big O of in a log n time in a worst case scenario, and in case of a best case scenario it is big O of 1. Now why we are thinking about this insert operation? Because in case of a heap sort, we have to, obviously we don't need to insert any node, but we have to sort them somehow. How we can do that? You see,